So here's part 2 of this problem. So we have a tent shaped like a triangular prism, and the floor is 4 by 6, and the triangular ends are isosceles triangles. Well, that's gonna help us draw this picture. So let me draw the isosceles triangle first. This length is 4, and it goes back like this, and this is 6. And there's our little pop tent. So let's look at the the volume of this guy is going to be 60, and that's going to help us solve for this height here, because the volume for a prism is just going to be the big base, right? The area of this big base times the height, and the area of this big base, let me do it a little bit. Let me put that H there. Oh, and I realize let's call it D instead, because I don't want to confuse the H's. So we're going to call this distance from here to here D, and if we had the area of the big base, which is this triangle right here, we just multiply that by 6. We don't know it, but what we do know is it's the area of that base is going to be 1/2 times 4 times D. That is the area of the base, right? Because it's a triangle, and the length, the H right here is the 6. So times 6, and we know that that has to equal 60. That's one of the givens, 60 cubic feet. Okay, so let's simplify this. 2 cancels with 4, leaves us 2. And so right now we have 2 times 6 times D, which is 12D, is equal to 60. So D has got to equal 5. That helps us with this part. Now we can do the, let's get the surface area, which would be 2 triangles, right? We have face 1, triangle 1, and we have another one back here that we can't see. So those 2 triangles, and then these 3 faces, the bottom, this side, and the other side. So first the 2 triangles, so triangle 1, this triangle 2 is, each are going to be 1/2 the base, 4, times the height, 5. And it's going to be 2 of those, right? 2 triangles. So that's 20. So we have 20 from the triangles, the ends. The base is 4 by 6. So the base of the tent, not the base of the prism. The base of the tent is 24. And then what about each one of these sides? The one we can see here. We can see this one, and then there's the other one that's back here that we can't see. Okay, what about that one? Well, that we're going to have to use the Pythagorean Theorem for, because we don't have this distance. And so what is that? What is that distance? Well, if we know that D right here is 5, and this is 2, this diagonal distance is to be the square root of 5 squared plus 2 squared. So that's just the Pythagorean Theorem. So I'm going to call that S. It's kind of like a slant. S is equal to the square root of 5 squared plus 2 squared. That's 25 plus 9. So square root of 34. And I'm going to call that 6. I'm rounding, and it could be a little bit better, but I don't have a square root function, so So if it's 36 by square 6 by 6, okay, so it's about 6. So again, this is just a rectangle. It's a 6. So we just said that this length is 6. It's a 6 by 6 rectangle, and there's 2 of them. So it's going to be 72 for the sides, for a total of 116 square feet. I hope you followed that. So here we can fill this part out. 116 square feet. And what's the tallest person? Well, let me just redraw this base. This is 4 by 6. The tallest person that can get in here will put their head in this corner and their feet in this corner. And once again, this is the case for the Pythagorean Theorem. So the tallest person would go from here to here, and that distance is the square root of 6 squared, 36, plus 4 squared, which is 16. And this, so I'm going to call this P for person. That would equal, let's drag this, the square root of 52, which is like, let's say 7.1. So someone taller than 7 feet could fit in here. Let's go. I'm just going to just say it's 7 feet. You got to get the exact number because they want it near to the nearest 0.1, but let me leave that up to you. Now I will do number 3.